Welcome back, 7th grade scientists, to another explainer. We are diving right into an absolutely crucial lesson for your assessment review today. And the exact title of our explainer is The Wave Investigation Lab Data and CER Video Overview. Just to make 100% sure you're in the right place, our exact lesson ID is Science, Physical Unit 04, Lesson Pack 07, Lab Data Assessment Rehearsal Video Overview. All right, let's jump right in. Here's a quick roadmap of our agenda today. First up, wave misconceptions and truth. Second, gathering our lab evidence. Third, constructing your CER. And finally, step 4, transfer, waves in storms. Okay, starting with section 1, wave misconceptions and truths. Let's separate some fact from fiction. You know, it's actually incredibly easy to get your wires crossed when learning about basic wave terms. So let's set the record straight right off the bat and test your instincts with a really common middle school misconception. Here's the question. Do all colors of light travel at different speeds? Think about that for a second. If you're standing outside looking up at a rainbow, is the red light zooming to your eye faster than the violet light? If you guessed yes, hey, don't sweat it, it's a super common trap to fall into. But the actual answer is no. According to our NASA sources, all visible light travels at the exact same speed. The speed is completely constant. What actually changes to make each color unique isn't the speed at all, it's their specific wavelength and their frequency. Before we get into the lab data, we absolutely have to get our physical wave measurements locked in. It's really fascinating how the National Oceanic and Atmospheric Administration, NOAA, defines these two easily mixed up terms. Wave height is just the vertical distance from the very top of the wave, which we call the crest, down to the very bottom, the trough. Wavelength, on the other hand, is the horizontal distance between two successive crests or two successive troughs. So remember, height goes up and down, but wavelength goes across. Moving right along to section 2, gathering our lab evidence. Let's analyze some data from our simulations. Whenever scientists use physical models, whether you're shaking a long clothesline like in the NASA activity, or you're using the PhET wave on a string simulation on your computer, you're providing what we call a mechanical input. And the fundamental rule here is that your mechanical inputs affect the wave properties. If you shake that string harder or faster, your physical input directly changes the wave's amplitude and its frequency. Basically, you are the one controlling the energy of the wave. So let's look at the actual evidence we gathered in the NASA Roy G. Biv tape experiment. In this lab, students used an adding machine tape marked with different colors to represent the different wavelengths of light. Notice the really specific data points we gathered here. For the color red, the marks were spaced 14 centimeters apart. For green, the spacing was 10 centimeters, and for violet, that spacing dropped down to just 8 centimeters. This distinct mark spacing drawn for each color perfectly acts as a physical model for the specific wavelength of each color of visible light. Now for section 3, constructing your CER. Let's build a rock-solid scientific explanation. I know, writing a formal scientific explanation can sound a little intimidating, but trust me, it is completely manageable for any 7th grade scientist when we break it down into 3 simple steps. Step 1 is your claim. That's the main statement or conclusion you're making. Step 2 is your evidence, the actual hard data you collected that supports your claim. And step 3 is your reasoning. This is where you explain exactly how and why that evidence supports the claim using scientific principles. Let's kick things off with step 1. Here is the explicit claim for our wave investigation. Claim: different colors of the visible spectrum have constant, distinct wavelength to frequency relationships. As we just saw in our tape data, red has the longest wavelength, while violet has the shortest wavelength. They each have their own unique fingerprint, so to speak. Next up, we need the evidence to back that claim up. What was our exact physical input in the lab? Well, our evidence comes from tallying marks on colored tape as it was pulled through a manila folder. Remember that setup? We watched the marked paper tape pass through a little window cut into the folder, and we counted how many wavelength marks passed by in a set amount of time. That physical tallying right there, that is our hard evidence. Finally, we have the glue that holds it all together: reasoning. We connect our claim and our evidence by pointing out a perfect inverse relationship pattern. Simply put, as wavelength decreases, frequency increases. Think back to our tape lab. The violet marks were only 8 centimeters apart, a really short wavelength. Because they were packed closer together, way more of them passed by the window in the same amount of time compared to the red marks, which were spaced 14 centimeters apart. Therefore, A shorter wavelength directly equals a higher frequency.
Now, any good scientist will tell you that we have to account for limitations. As the NASA lab instructions specifically warned us, quote, try to pull the tape at about the same speed for every trial. Since human hands were pulling the tape through that folder, the pacing is never going to be perfectly robotic, and that introduces human error into our data. Think about it. If you accidentally pull the tape faster on the violet trial, your frequency tally is going to artificially jump up.
So, how do we fix that? We use human and evidence checks to verify our data's reliability. Instead of just pulling the tape once and calling it a day, you conduct 3 separate trial runs, and then you calculate the average number of wavelengths observed. Averaging those multiple trials helps smooth out that manual pulling uncertainty and gives us a much more accurate frequency measurement. Which brings us to Section 4, Transfer, Waves and Storms. Let's apply this knowledge to the ocean. We've mastered these concepts using string and paper tape in a lab, right? So let's scale this up with some real-world ocean dynamics provided by NOAA. What actually happens to basic wave properties when intense energy from a massive storm is introduced to the ocean? Well, the wave shifts dramatically. First, wave heights increase. Second, wavelengths decrease. NOAA notes that during a storm, wavelengths can become highly compressed, with some dropping to as small as 15 meters, or about 50 feet. It is a massive influx of energy that fundamentally changes the physical dimensions of the wave itself. And to really anchor this transfer concept in a memorable real-world measurement, think about the number 10. According to NOAA, wave heights during storms may exceed an astonishing 10 meters. To put that in perspective, that is 33 feet high. Understanding the specific relationship between wave height and energy is absolutely crucial, because it helps scientists predict just how dangerous these waters will be for boaters and surfers. And here we are at Section 5, Final Thoughts and Overview. Let's wrap up this rehearsal. You have done an absolutely incredible job mapping out these concepts today, going all the way from paper tape in a classroom to the raging ocean. We've measured colored pencil marks, and we've analyzed 10-meter storm waves. We've seen firsthand how understanding basic wave mechanics basically unlocks the universe, since waves exist in the light we see, the sounds we hear, and even the Wi-Fi we use every day. You have successfully completed your review explainer for the Wave Investigation Lab, Data and CER Video Overview. And for the record, that exact lesson ID one more time is Science, Physical, Unit 04, Lesson Pack 07, Lab Data, Assessment Rehearsal Video Overview. Excellent job today, scientists. So I'll leave you with this final thought. What hidden wavelength and frequency patterns will you discover next when observing the world around you?